All right, so this lesson, again, looking at some of the more standard initial applications of integrals, involves using integrals to find volumes, volumes of solids. And these often involve the idea of a two-dimensional shape being rotated into 3 dimensions. And shapes like this we can actually quite nicely use integration to find their volumes. And so let's start with this example here. I have this graph right here of root x. But we have it only from 0 to 1 in the x. So imagine this region here from 0 to 1 of root x. Well, imagine if that region now is rotated around the x-axis. And that's what you're kind of seeing in this visual here. And if you rotate this around the x-axis, you create this shape you see right here. It's not a cone. It's just, I'm sure there's some fancy name for it. But let's call it a solid. You have this shape here. So we can find the exact volume of this using integration. Rather pleasantly, actually. And the idea is we want to imagine, if I zoom in on here, this solid being composed of a whole bunch of circular disks, like it's drawn here. And each of these disks, you know, if it's a circle, I can find the area of the circle times the thickness. And, you know, just like when we first started talking about integration, we imagine finding the area under a curve with a bunch of rectangles. Well, I can approximate the volume of this with a whole bunch of disks. But the skinnier these disks are, and therefore the more of these disks I have, the closer my approximation becomes to be an exact value. And if the change in x there, as it approaches 0, I have infinitely many, infinitely skinny disks that are really just circles with an infinite thinness, I guess I could say. Then altogether, add that all up, I have the total volume. So that's the sort of idea behind this. And so in principle, to work this out, is I need to, if I can find the area of just any one of these disks with respect to x, I can add all these things up. So if I look at this disk right here, the radius is, in this case, always the same as the output of this curve root x. So remember, this curve here was y equals root x. And really, your y coordinate is the same as radius. So the radius of all these disks is the same as root x. And so that means any one of these circles, this circle here, the area of it is the same as pi times the radius, root x squared, or just pi times x. So pi times x represents the area of any one of these circles in 3 dimensions going along here. And so the idea is I now want to find the sum of all these infinitely skinny circles from 0 to 1, which means I want to find the integral. From 0 to 1, because that's, again, the bounds of this shaded region, or the bounds of my 3-dimensional object, of the area, which in this case is pi times x dx. Right there, that will tell me the volume exactly of this. Keep in mind again, maybe I'll just write this in red. Pi times x, that represents the area of any one of these disks. Dx represents the thickness of any one of these disks, so like little cylinders that are incredibly skinny. And as dx approaches 0, there's infinitely many of these little disks, and add them all up, you got the total volume. And this is really easy to integrate, especially if I pull out that factor of pi and rewrite this as pi times the integral of 0 to 1 of just x dx. Well, let's say I'm pretty much done. I'm going to be done in a few seconds now. So the integral, the antiderivative of x is 1/2 x squared. I might as well write this as pi over 2 times x squared and evaluate it from 1 to 0. And you can see now this is just going to equal pi over 2. Units cubed. So that's the exact volume of that weird 3-dimensional shape. And so the idea in this case is far more abstract or far more challenging, I think, than the execution. In this case, you can see all the work. And the idea, again, is that we want to find, in this case, area of all these circles. And once we know how to find the area of any one of these circles with respect to x, we find the integral. We add up all these together, and that tells us the volume. And now using this, we can actually prove a formula you may or may not be terribly familiar with, which is a formula for the volume of a sphere. And so the formula for the volume of a sphere, you've definitely learned before, and you may have forgotten, is 4/3 pi r cubed. We can now prove where this comes from relatively nicely using what we just saw here. And this is one of the very, very old formulas in mathematics here, and we can kind of prove where it comes from. And the idea is, well, we're going to kind of follow the same idea, but I give you a little, I give us a bit of setup here. The volume of a sphere can be evaluated using either of these integrals. So what I have here, if we have a radius of r, then I can imagine I have a sphere here where one end is at minus r, one end is at positive r. And I have, again, all these little circles that move along. And as I move along from left to right, and I have all these circles, I add up their total areas, because they're infinitely skinny, that would tell me the volume. And that, what I've just described, is what you see for this first integral right here. However, spheres are definitely symmetrical, so it would be a little easier is to imagine just half this sphere. Just imagine it starting at 0. And find just the volume of this region here, which is from 0 to r, instead of net minus r to r, and then just double it. And that's just a bit more pleasant. Plus 0 is a lovely number. It's pretty easy to work with the number 0. So I'm going to think about this. Again, taking into account the symmetry of things. OK, so with that said, let me go back to my diagram here. And conveniently enough, there's already kind of a nice visual of the three-dimensional object here. So we need to figure out how can we find the area of that disk, no matter where it is, with respect to x. Because again, I want to integrate from 0 to 1, or 0 to r, sorry, I should say, which is, I'm looking at it this way. Now, why can't I look at it vertically? I can, but it's more common to think about it this way. That's why. But I mean, it's a circle. Sorry, it's a sphere. I can look at this in many ways. So the area of that circle there, is the same as, pi r squared. But in this case, the radius is the same as the y value. So to not make this get too messy, that's my radius. I'm going to draw that in red. And again, it's my y value. So I need to think about what that is with respect to x. How is the radius, or how is y related to x? Because again, if I look at my integral here, I want to integrate this with respect to x. And so it's pretty pleasant to think about how I can connect x and y together, because I'm dealing with a circle. And you can see this diagram here hopefully reminds you that x and y are related through the radius, and x squared plus y squared must always equal r squared. And so I can say here that the area of that circle with respect to y is pi times y squared, but I want the area with respect to x. And so to figure out that, I need to think about, again, x squared plus y squared always equals r squared. So if I solve for y squared, I get r squared minus x squared, which means I can substitute that y squared there with r squared minus x squared. And that there, pi times r squared minus x squared, that represents the area of any one of these disks. All right, and now, so that's my area function. And now I want to integrate that from 0 to r, and then eventually double it. Because again, I'm really focusing on just half the sphere. And so let's find the integral. We'll double it eventually from 0 to r. Again, I want to just stick with r because I want to eventually come to that general formula for this volume of a sphere of pi times r squared minus x squared times dx. And at this point, why don't I pull out that that constant of pi. So I'll write it as 2 pi times 0 to r of r squared minus x squared. Keep in mind, r is a constant. Right? R is the radius of the sphere. And so with that said, I can now integrate this. R squared is a constant, like I keep saying. And so the antiderivative of r squared is r squared times x minus the antiderivative of x squared is x cubed over 3. And now I can evaluate this integral from r to 0, or 0 to r. So if I do that, replacing, again, I'm replacing x with r, and then x with 0. So if I replace x with r first, I get r squared times r minus r cubed over 3 minus just 0. So I don't need to bother writing that part down. And then you can probably see where I'm going with this. Here I have r cubed minus r cubed over 3. Let's find a common denominator there. Find that common denominator, and I have 3r cubed minus r cubed. Collect like terms. I have 2r cubed over 3. Put this all together, and I have 4 times pi times r cubed all over 3, or 4/3 pi r cubed. All just as good. And again, I knew the answer from the start. It's just trying to prove how we can get there. All right, and so keep in mind, most of my work was just simplifying some rather simple equations at this point. The actual integration part wasn't challenging. And honestly, that'll be the case for most of these questions. The actual integration won't be so challenging. It's how do we get to a point that we know what to integrate. All right, last one. And kind of similar to the last question in the previous lesson, in which we'll want to think about this integrating with respect to y instead of integrating with respect to x. But this time we have this object, this region, sorry, that's shaded in orange. And this is the region between x cubed and the y-axis. But this time we want to imagine this being rotated around the y-axis. And so if it gets rotated around, you have some sort of shape like this. And it would look, you know, this, you can kind of see this sort of three-dimensional object that would be created. And so I want to integrate this vertically from this lower bound of 0 to an upper bound of 8. Because I want to add all these circles vertically from these small ones at the bottom all the way up to the top. And again, that would tell me the total volume. And so I need to think about what is the area of one of these circles. Let me zoom in on this a bit. Focus on, oh, I got rid of a little too much. There we go. All right, so if I look at just one of these circles, the radius is the same as the x coordinate. But like I said, I want to differentiate, I want to integrate with respect to y. And so I need to think about what the radius of any of these circles is with respect to y. Well, the good thing is that equation there tells me how x and y are related. And so if y equals x cubed, then y to the power of 1/3 equals x. And so y to the 1/3 must also equal the radius of any of those circles, because of what I said right here. X equals r, x equals r. And so now I know what to integrate. I want to integrate vertically, so from 0 to 8, all these little circles, pi times the radius squared dy. And the radius each time is y to the 1/3. All right, and like I said, the hard part will quite often not be the actual integration, it's getting to this point. So now the question I think is, the hardest part is done. That's it before integrate. Let me do a few things. Let's take out that factor of, or that constant of pi, and write this as y to the 2/3. use the power rule. We get 3/5 times y to the 5/3. And I want to evaluate this from 8 to 0. And at this point, you probably don't really need to watch me do this, but I get pi times 3/5. Now I will say without a calculator, 8 to the 5/3 is not nearly as complex as it seems. 5 power 5/3 means you're cube rooting and raising to a power of 5. So the cube root of 8 is 2. 2 to the power of 5 is 32. And so I have 32 times 3/5 minus 0. And so in the end, I have 96 pi over 5 cubic units for that region. All right, so notice all three of the examples from today, I will never say are easy, but all three of them, once we had the integral set up, like once we were right here, once we were right here, and once we were right here, we had the hardest part done, in my opinion. In fact, we didn't even have to use integration by substitution at all today. Isn't that nice?